Hello, people. It's your boy. We have this paper too, and we're going to tackle it. A couple of things before we start here. I can't really upload the paper because I'm not supposed to, but I can go through the answers and I'll refer to the question numbers as I do that, just so you know which question I'm referring to. Of course, we're going to start with question 1, 1A. Maybe I'll change. Actually, this is good. 1A. I'll just read the question, follow along with me. But a student determined the percentage of the active ingredient, magnesium hydroxide, in a 1.24 gram antacid tablet. The antacid tablet was added to 50 cm cubed of 0.1 mole per decimeter cubed of sulfuric acid, which was in excess. So calculate the amount in moles of H2SO4. Okay, well, we have the molarity and we have the volume, and that's really all we need to calculate the moles. So it is given to us in centimeters cubed, but we want to convert that to decimeter cubed. So what we really have is this, right? Divide by 1,000, decimeter cubed, times our molarity, which is just this, right? Of H2SO4. This was given to us in the question, and the reason we converted to decimeters cubed is because we want these two things to cancel out, leaving us with moles. And so to the proper amount of sig figs, that's just this, 0.00500 mole H2SO4. Okay, so the next question, B, formulate the equation for the reaction of H2SO4 with MgOH2, or Mg bracket OH squared, or 2, subscript, not superscript. And so if you remember, this is actually just an acid-base titration. It's an acid-base reaction. And the outcome of any acid-base reaction is a salt and water. So let's do this. So we have H2SO4. And I don't believe you need to have your state symbols, but I'll put them in anyways. So H2SO4 plus MgOH squared, solid, gives us, well, our salt would be MgSO4. This is a 2 plus, 2 minus, so the charge balances out there. This is aqueous. And then H2O. Now we have to do the little check. Is this balanced? Well, let's ask ourselves that. Is it balanced? Well, I'm looking here, and we have one Mg here, we have one Mg here, we have one SO4 here, we have one SO4 here, we have two H's here, we have two H's here. Oh no, we don't just have two H's here, we also have another two H's, so we have four H's, which means if we want to balance it out, we need a 2 here. So we have four H's here now, we have four H's here now, and the O's also also balance out. There's two O's on this side, and there's two O's on this side. So that means we've done a good job balancing this. Now let's move on to the next question. Let's move on to the next question, C. The excess sulfuric acid required 20.8 cm cubed of 0.1133 molar NaOH for neutralization. Calculate the amount of excess acid present. So this looks like a back titration to me. The excess sulfuric acid, Okay, so one thing we actually need to know is, well, now we have excess sulfuric acid reacting with NaOH. That means we need to know the equation for which this neutralization between H2SO4 and NaOH occurs, because we're going to need their molar ratios to move on with the question. So we have H2SO4 plus NaOH, and we know this gives us a salt and water, so Na2SO4, okay, plus H2O. And of course, we're going to want to balance this out. There's two NAs here, but there's only one here, so we're going to put a 2 there. And we're going to ask ourselves, well, are the hydrogens balanced out? Or they're not, because there's 4 on this side and there's only 2 here, so we're going to put a 2 there. The O's are now balanced out as well, because there's 2 here and there's 2 there. Okay, so it's balanced out now. Next thing we need to do, if I can erase this here, is we need to ask ourselves, well, I used how many moles of NaOH? Well, it gives us the volume and it gives us the molarity of NaOH. So we can do the same thing we did in part A by the same, principle. We're going to convert our volume to dm cubed so we can cancel out for moles. We're going to multiply this by our molarity of NaOH. I forgot to put the units. This is dm cubed. And if we multiply this, really, well, this cancels out. We get the amount of moles we need in order to, or well, amount of moles for NaOH, but we're not interested in NaOH, we're interested in H2SO4. So we know that this is NaOH, but we want to get to H2SO4. So we need to do our handy mole bridge. So this is 2 moles NaOH, right? There's a 2 coefficient here. And then we also have a 1 coefficient here in front of the H2SO4. And so if we cancel out, well, NaOH can go bye-bye here and here. And we're left with moles H2SO4. And then this will give us 1.178 times 10 to the negative 3 moles H2SO4 in excess. Okay? So for D, what we're going to do is, well, let's calculate the amount of H2SO4 that reacted with MgOH squared. Or, oh, I can't believe I said that, MgOH, or magnesium hydroxide. And to do this, all you have to realize is, well, you're going to subtract from the total amount of H2SO4 that we calculated in A, the amount we calculated in C. And so, really, this is used H2SO4 is equal to 0.00500 mole, because that's the total amount of H2SO4 we had. Then we're going to subtract from that the amount that was in excess, which we calculated in C. And our result should be the amount we've actually used, which is 3.82 times 10 to the negative 3 moles of H2SO4. So for E, we're asked, determine the mass of MgOH in the antacid tablet. Well, we know how much H2SO4 we used, and we calculated in B the relationship between H2SO4 and MgOH, so we can use a handy mole bridge to help us out here. So we have the amount we've used in H2SO4, 3.82 times 10 to the negative 3 mole H2SO4. And now we need to use the mole bridge to get to the mole MgOH. So if we go back here, there's a 1-to-1 ratio. So we have a 1 mole H2SO4. And then our ratio as well, 1 mole MgOH. And really, this leaves us with moles MgOH, but we're not done there. We want to determine the mass. So we now need to use our relative molecular mass, which if you calculate for MgOH or magnesium hydroxide is 58.33, because you add Mg plus 2 oxygens plus 2 hydrogens. And your answer should be 0.223 grams of MgOH. Okay? So that's E for you. And so if we go to F, I realize this might be a long video because I'm taking my sweet time. Calculate the percentage by mass of magnesium hydroxide and the 1.24 gram antacid tablet. Well, we know that the amount of MgOH in the antacid tablet is 0.223, and the total mass of the antacid tablet is 1.24 grams. We multiply this by 100 to get a percentage, and that should give us to three significant figures, 18.0%. All right, so for G, outline why repeating quantitative measurements is important. This is more, I'm not going to write it down. This is more of an IA question, maybe paper 3 type question, but really, if you repeat quantitative measurements, you can get an average, and this average delineates from the amount of influence a random or systematic error can have on your final results. Because if you only have one trial, then the influence this error has on the final result is comparatively large. But if you do this result, or if you do the experiment over and over again, hence, or in other words, just doing or increasing your trial number, then you can get an average, and the absolute error, or just in general, the error the apparatus or random error in the environment has on your final result is a lot less. Yeah. So let me flip the page here, and we're going to move on to 2 now. So I guess here I'll just say repeat trialing / average. That should be your gives us more reliable outcome, because random or systematic error has less of an influence on our answer, because again we've taken an average. Okay, so question 2, 2A, sketch a Maxwell-Boltzmann distribution curve for a chemical reaction occurring or showing the activation energies with and without a catalyst. So if you remember what a Maxwell-Boltzmann distribution is, it really just shows the fraction of molecules distributed along different energies. So your x-axis is going to be energy, and then your y-axis is going to be fraction of molecules or atoms of molecules. Okay? So conventionally, your Maxwell-Boltzmann distribution is going to have a large amount of particles with not that much kinetic energy, and then distributed over the increasing energy, less and less particles. So in other words, typically we have a ton of molecules with lower energy and comparatively fewer molecules approaching this higher energy level. But we never touch the x-axis, right? There's never essentially a point where there are no molecules being analyzed. So it's never going to touch the x-axis. So if you remember what an activation energy is, it's essentially the amount of energy required to ensure a chemical reaction occurs. So when 2 molecules collide, they need to collide with an energy greater than or equal to this activation energy in order to continue to happen or continue to form a product. So conventionally, you can put the activation energy anywhere near the higher energy level or higher energy end. But when we're graphing the catalyst, we need to make sure that the activation energy is less, because the definition of a catalyst is essentially any substance which is capable of reducing the activation energy needed for a reaction to actually occur without itself actually being consumed in the reaction. So this means that if this is the activation energy of the uncatalyzed reaction, so uncatalyzed, then with the catalyst, there should be a larger proportion of molecules which are capable of reacting or capable of colliding in order to form a product. So this is catalyzed. Okay, so B, excess hydrochloric acid is added to lumps of calcium carbonate. This graph shows the volume of carbon dioxide gas produced over time. So I'm going to draw the graph you see on your paper because I don't have it here. So you have volume of CO2 and then you have time. And you have this dotted line that the test shows. And so it asks you to sketch a curve of on the graph to show the volume of gas produced over time if the same mass of crushed calcium carbonate is used instead of lumps. So keep in mind, you're not changing the concentration of the HCl, or you're not changing the amount of calcium carbonate being used, you're just changing its surface area, which means that you're going to produce the same amount of CO2, but the rate at which this occurs is much faster. So you're going to have a very steep incline to indicate that the majority of the reaction happens in a much lesser time, but it's going to plateau at the same level of CO2 because no additional CO2 is going to be produced by increasing its surface area. So that's what you'll get. Okay, state and explain, and I don't think I'm going to write this down, I'll just talk about it, but state and explain the effect on the rate of reaction if ethanoic acid of the same concentration is used in place of hydrochloric acid. Well, remember, ethanoic acid is a weak acid, hydrochloric acid is a strong one. This means that HCl much more readily donates a proton than ethanoic acid. And so what you'll get is a slower rate of reaction for ethanoic acid because it's weaker and less readily reacts. Outline, for C at least, outline why pH is more widely used than H+ for measuring relative acidity. Well, when we measure the concentration of H+, our molarity is usually a very small number. So when we take the negative logarithm, or the p-value of our H+ concentration, we get a larger number that is more convenient to work with. We're not getting any weird magnitudes of 10, but we're getting a whole number that is just easier to use. Just seeing if I've covered everything I should say there. Yeah, pretty much it. I mean, with the HCl and ethanoic acid, you just want to make sure you talk about the fact that ethanoic acid doesn't readily and fully dissociate, whereas HCl just about completely dissociates, which is why the reaction actually occurs much faster with HCl. Okay, so if we go to question D1, if we go to D1, after all that explanation, the graph represents with the titration of 25.00 cm cubed of 0.1 molar aqueous ethanoic acid with 0.1 molar aqueous sodium hydroxide. Deduce the major species other than water and sodium ions present at point A and B. So this is D1. Okay, so at point A we have, we don't have our full equivalence point, but we have our half equivalence point. And what this means is that, well, we've gotten halfway to our titration endpoint, yes, but we have equal molar amounts in solution of our, in this case, CHCOOH, which is the weak acid, and its strong conjugate base, CH3COO minus. And you might be like, well, why is that? Well, this is a weak acid, strong base titration. And so at the half equivalence points, we have NaOH reacting with CH3COOH. But only half of this, well, let me try and do a better job here. Well, we know the equivalence happens at 25, so say this is 25, and we know that half equivalence occurs at 12.5. This gives us really CH3CO minus plus Na plus H2O. Now, at half equivalence, only 12.5 NaOH is used, which means that, okay, this 12.5 is used up. 12.5 from 25 is still 12.5, and now we have 12.5 of CH3CO minus, which means at half equivalence, we have equal molar amounts, or equal amounts of CH3 H3COH, the weak acid, as well as its relatively stronger conjugate base, CH3COO minus. So those are the two major species that have equivalence. Now at B, this is where complete equivalence happens. This is where equivalence point is. And at equivalence point, all you have is a salt. Now in this case, the salt that is present in this reaction is CH3COONA. But because this is an ionic solution, or it's a salt in solution, it dissociates into these two products. And the question specifically tells us other than water and sodium ions. So we can ignore this, and so the real main answer for B is just the ethanoate ion. So let's move on to the second part of this question. Calculate the pH of 0.1 molar aqueous ethanoic acid given Ka. Given Ka. So we need to first ask ourselves, well, what is the dissociation, the equation of dissociation for the ethanoic acid? Well, first of all, it's a weak acid, so it doesn't completely dissociate, but what we get as products is the ethanoate ion and H3O plus. Now you can also put water here, but remember the Ka constant is modified equilibrium constant, which already accounts for water, so it doesn't really matter. But Ka, the acid dissociation constant, is equal to the concentration of the ethanoate ion times the concentration of the hydronium ion, or just H plus, over the concentration of the actual ethanoic acid itself. Now, an assumption we can make is that because the autoionization of water is so negligible, we can just say that these two concentrations are effectively the same because their coefficients are also the same. So this just means that Ka is equal to the square of our hydronium ion concentration over our ethanoic acid concentration. And we do know a couple of things. First of all, we know what the concentration of our ethanoic acid is 0.1. And we also know what our Ka is. It's 1.74 times 10 to the negative 5. But we don't know what H3O plus is, okay? But we can do a little quick algebra, and we find out that H3O plus is equal to, if we do a quick algebra, the square root of 1.74 times 10 to the negative 5 times 0.100. I'm not going to calculate the exact answer, but we know that if we know H plus, we can very easily calculate pH, because pH is just the negative logarithm of whatever this is, and what I got was 2.88. So if you plug that into a calculator, you'll get 2.88. Now, the third part of this question is, outline, using an equation, why sodium ethanoate is basic. Well, if we think about it, the ethanoate ion, or the ethanoate ion, yes, is the strong conjugate base of ethanoic acid, the weak acid, because again, if you have a weak acid, you have a strong conjugate base. If you have a strong base, you have a weak conjugate acid, and you vice versa. So what we really have is, well, CH3COO minus, our ethanoate ion, plus H2O gives us CH3COOH plus OH minus hydroxide ion. So we release hydroxide in solution because this strong base takes the proton donated by H2O, our bronzosylate acid in this situation, to form this weak acid, but also consequently release a hydroxide ion, which makes our solution basic. So question 4, I can't read Roman numbers. Predict whether the pH of an aqueous solution of an ammonium chloride will be greater than, equal to, or less than 7. Okay, so let's think about this. Ammonium is a comparatively stronger, well, we really need to ask ourselves, what's ammonium chloride made from? Well, likely HCl and NH3 plus, okay? Or NH3, sorry. This will give us ammonium chloride, which is NH4Cl. Now, HCl is it's a strong acid, right? Which means that Cl minus, its conjugate, is actually a weak base. Conversely, NH3 is a weak base, which means NH4 is a comparatively stronger acid. So if we ask ourselves this question, really, well, I guess NH4 is a stronger acid, so what happens is that this NH4 is going to react with H2O to form NH3 and H3O plus ions. And because we're releasing hydronium, we're actually decreasing the pH and making the solution more acidic. Okay. Well, I guess in terms of this question, we don't want to say acidic. We're going to say less than 7. So I was just reading that question over again. Just make sure you're answering with the precision or the level of precision that the question is being asked, just so they don't dock marks. But say that it's less than 7. Don't say it's acidic. Okay, let's go to question E. Question E. So the first part, formulate the equations for the reaction of nitrogen dioxide, NO2, with water to form two acids. So this is in the acid deposition part of Cognity, if you remember that from a while ago. But essentially, NO2 can react with water to form HNO2 plus HNO3. Now this, of course, isn't balanced because we have 5 oxygens on this side, but we only have 3 here. So we're going to up in the ante. I'm going to put the 2 here because we also need 2 nitrogens on this side. So we're going to do the little check. We have 2 nitrogens here, and we have 2 nitrogens here. We have 5 O's here, and we have 5 O's there. And lastly, we have 2 H's here, and then we have 2 H's there. So it works out. Now let's look to the second part of this question. Formulate the equation for the reaction of one of the acids produced in EI with calcium carbonate. So I'm going to choose HNO3, and it's going to react with CaCO3. And remember, when we're reacting with a carbonate, our products are CO2, H2O, and the salts. So this is what we need to make sure we see in our final reaction. So the salt that's formed is Ca3 or CaNO3 2, because the charge on Ca is 2, the charge on NaO3 NO3 is 1, and you do the little switcheroo and you get 2 as a subscript on the NO3 and you get a 1 as a subscript on the Ca. You also have H2O and CO2 you have to account for, and then all it is a game of balancing. So right away I see that the H's aren't balanced. There's 2 H's here, but there's only 1 here, so I'm going to throw 2, and we're going to ask ourselves if this works out. So how many calciums do we have here? We have 1, we have 1 here as well. How many N's do we have on this side? We have 2. Do we have 2 here as well? Yes, we have 2. So the N's check out. How many O's do we have on this side? We have 6 plus 3, we have 9. Here we have 6 plus 1 plus 2, which is also 9. And then the C's also work out, so we're chilling. All right, so question 3. Isn't this so fun? Why is this taking forever? Question 3. Draw the first 4 energy levels of a hydrogen atom on the x-axis, labeling n equals 1, n equals 2, n equals 3, and n equals 4. So we're going to draw our axes, well, just really 1. And so we have our energy, and we also need our energy levels. Now, they ask us up to n equals 4, so we're going to do that. We're going to start at n equals 1. We're going to go to n equals 2. However, remember that energy levels are convergent and concentric. So the distance between n equals 1 and n equals 2 is much larger than, or it's about twice as large as the difference between n equals 2 and n equals 3. So you have to draw this a bit closer. And then n equals 4 must be a bit closer because they're convergent. And so question 2, or the second part of this question, asks us to draw the lines that represent the electron transitions to n equals 2 in the emission spectra. So this isn't too hard. Well, if we go to n equals 2, the only two levels we can do this from is from n equals 4 and n equals 3. This is where electron excitation may happen. So electrons going from the excited state to the ground state, where the ground state is n equals 2. And now we have a little bit of a frequency question. Hydrogen spectral data give the frequency of 3.28 times 10 to the 15 s to the negative 1 for its convergence limit. This is not part of the question, but let me define what a convergence limit is. The convergence limit is the highest energy end of a series of spectral lines. So when an electron transitions to the convergence limit, the amount of energy this absorbs is actually exactly the same as the first ionization energy, because the electron is transitioning to the infinitieth shell. There's actually infinity shells because, again, energy levels are convergent and concentric. They never end. So essentially what the question is asking you is to find the ionization energy. And you might be like, well, what's the relationship? Well, I just said it. If we know the frequency of an electron transitioning to the convergence limit, we can technically calculate its ionization energy because those two things are one and the same. So let me pull out the data booklet, which says that E is equal to hv, where V is our frequency, h is Planck's constant, and E is the energy we're attempting to find. So if you look at your data booklet, I think it's section 1, we see that Planck's constant is equal to 6.63 times 10 to the negative 34 joule seconds. And then we know that frequency is 3.28 times 10 to the 15 s to the negative 1. And I calculated this already, but what I got was 2.17 times 10 to the negative 18 joules, okay? So IV, question 4, let's get it. Calculate the wavelength in meter for the electron transition corresponding to the frequency in A using section 1 of the data booklet. Okay, so section 1 gives us that C is equal to wavelengths times frequency. So if we rearrange for wavelengths, we get that wavelength is equal to C over V, where C is just the speed of light, which is 3 times 10 to 8 meters per second, over V, which is what the question gave us, essentially, 3.28 times 10 to the 15 s to the negative 1. These bad boys cancel out, and then we're really just left with 9.15 times 10 to the negative 8 meters. So these questions are just a bit more about knowing how to use the equations given to you by the IB in the data booklet. Free marks, in my opinion. Let's move on to B. Okay. Elements show trends in their... I'm not going to write this down. I'm just going to explain it. Elements show trends in their physical properties across the periodic table. Okay. Outline why atomic radii decrease across period 3, sodium to chlorine. So if we move from left to right across from sodium to chlorine, what we see is an increase in proton number because there's an increase in the atomic number, which means that there is an increased positive charge in the nucleus. The amount of shielding electrons, which are electrons between the nucleus and the outermost valence electrons, remains constant, which means that there's a net increase in the effective nuclear charge of these elements moving from left to right. With an increase in the effective nuclear charge, electrons on the outermost valence shell move closer to the nucleus, which in return decreases the atomic radius, moving from sodium to chlorine. So that's a 1-mark question. You can truncate what I just said into one sentence. For 2, outline why the ionic radius of K+ is smaller than that of Cl-. While both are isoelectronic, so K+ and Cl- have the same amount of electrons, K+ has more protons than Cl-. This means that the effective nuclear charge of K+ is greater, but there's also the same amount of electrons, which means that the outer electrons on K+ are more attracted to the nucleus than those electrons of the Cl-, overall decreasing the ionic radius of K+ more than it does Cl-. Okay, let's move to C. Copper is widely used as an electrical conductor. Draw arrows in the boxes to represent the electronic configuration of copper in the 4s and 3d orbitals. Now, IB is trying to be sneaky because copper is actually one of the exceptions you're expected to know in terms of electronic configuration. Now, by Aufbau's principle, essentially, the 4s orbital, essentially, should be filled completely before the 3D. Now, if you look at your data booklet, section 6 on the periodic table, you'll find that copper, if you follow the pattern, should have 9 valence electrons. Now, this is not true. It actually has 10. And this is because electrons are most stable when their orbitals are, or when the orbital is most stable, or the sublevel itself is most stable when it's either empty, half full, or completely full. So actually, instead of getting a 4s orbital with 2 electrons, we get it with 1, such that instead of having 9 in the 3D, one of these bad boys actually moves here, so that we have a stabler, energetically stabler atom. So that's what we get here. So 2, impure copper can be purified by electrolysis. In the electrolytic cell, impure copper is the anode, okay? So it's the positive electrode. And pure copper is the cathode, the negative electrode. And the electrolyte is, of course, copper 2 sulfate solution. Formulate the half equation at each electrode. So at the anode, remember, anode is the site of oxidation. It is the positive electrode as well. So essentially what's happening is that at the site of oxidation, copper, which composes the anode, the impure copper, is being oxidized into 2+ ions, well, in return releasing 2 electrons, okay? Now the cathode is the site of reduction, and in an electrolytic cell, it is negative. So Cu2+ in the electrolyte reacts with the 2 liberated electrons to form copper, copper solid, which is deposited on the cathode. Now, outline where and in which direction the electron flows during electrolysis. I'm not going to write this down. I'm just going to say it. So, of course, the electrons flow from the anode, the site of oxidation, to the cathode, the site of reduction, through the conductive wire. It's an external circuit. And so question 4, deduce any change in the color of the electrolyte during electrolysis. There's no color change because for every copper we're actually reducing, we're actually releasing a new copper ion at the site of oxidation in the anode. So for every replaced copper, there's one deposit. For every discharged copper from the electrolytic solution, from the electrolyte, new coppers are being released from the site of oxidation. So there's no color change. There's no net change in the concentration of the electrolyte. So deduce, question 5, deduce the gas formed at the anode when graphite is used in the place of copper. So let's think about this a little bit. Anode is the site of oxidation, okay? When we have a anode which is made of copper, copper will be deposited. Copper is what is being oxidized. But when that is when it is replaced with graphite, copper is no longer oxidized because it's no longer made out of copper. So what actually is instead oxidized is the actual H2O itself. Well, you might be like, well, if Cu2+ is still in the solution, can't it just also be oxidized? Well, no, because the CO2+ in the solution is already oxidized as 2+ ions, and also because H2O more readily oxidizes than Cu2+, and you can prove this to yourself using the table of half equations in your data booklet. But in brief, H2O is oxidized to form O2 when the graphite is used to compose the anode instead of the actual copper itself. So question D, explain why transition metals exhibit variable oxidation states in contrast to alkali metals. So remember, transitional metals have a 3D orbital, and these 3D orbitals are very close in energy to the 4s orbitals, which means the consequent and successive ionization energies between the 3D and 4s suborbitals are very similar, which means that there's almost no change in the amount of ionization, or there's no big leap in the change in ionization energies, which means you can keep removing electrons going into the 4s sublevel as well. However, with alkali metals, there's a huger or comparatively bigger energy difference between the s orbitals of the valence electron and the p orbital in the core of the core electrons. And so there's a greater disparity in the the first ionization energy, which means there's a far bigger energy jump, so that ionization can't happen as continuously as it might in a transition metal. So question 4a, formulate the equation for the redox reaction. And let me just draw it out for you so you know what I'm talking about here. We're going to do 4a, and the question already gives us the pre-made equations. So we have BrO3 minus, I should do the states. I should probably put the states in here, even though it's really annoying. Plus 6H plus 6E minus gives us Br minus plus 3H2O. And then we're also given 2I minus and then I2 solid, and then 2E minus. Now, in order to consolidate these two equations, we need to make sure we actually have the same electron counts. Now, notice here it's 6. So that means we have to multiply our entire lower equation by 3. So then this really just becomes 6, this becomes 3, and then this becomes 6 as well. So then the electrons really just cancel out. So our net equation now is Br3 minus plus 6H plus 6I minus goes to 3I squared. Oh, it's 3I2. Oh my goodness, I keep making that mistake. Plus Br minus plus 3H2O liquid. Awesome. So now B. Let's see what B is all about. We actually did this question before in our electrochemistry unit, but we'll do it again. The change in the free energy for the reaction under standard conditions, the change in Gibbs, is negative 514 kJ at 298 K. Determine the value of the cell potential in V for the reaction using sections 1 and section 2 of the data booklet. So we know that delta G can be related to our cell potential by negative NFE, where N is the amount of transferred moles of electrons, F is Faraday's constant, and E is the cell potential. And of course, delta C we'll have to actually we'll try and find. So we're going to isolate for our cell potential, and so we get delta G over negative NF. We know that delta G is in kJ, however, delta G is in J, so we have to multiply by 1,000 to the value given to us in the question. So this is really just this. I'm not going to say the numbers because I'm going to butcher them. I'm not in the mood to talk. We know that 6 electrons are being transferred because that is what we were told here. Times Faraday's constants. And then this should give us our answers in volts, which I got as this. Alright, 4C, let's get it. Calculate the standard electrode potential in V for the BrO3 Br reduction half equation using section 24 of the data booklet. Okay, so what I like to do to calculate E cell is use a nifty equation I think I made up. I'm sure someone else has used it before, but I just randomly thought about this. So I call it E red minus E ox. And the reduction reaction is, of course, well, the reaction of whatever is being reduced, and then E-ox is whatever is being oxidized. So we know that E cell, our cell potential, is what we calculated in B. We don't know what our reduction is, okay? We don't know what the reduction is, but we do know what the oxidation is, because it's in our data booklet. Well, if we look back at what's being oxidized, it's actually the I minus to I2, which is oxidation. And this value is actually given to us in the data booklet, so section 24, and it's actually 0.54. So if we do a little bit of algebra, we find that E red is equal to 0.88 plus 0.54, which is 1.43 volts. That should be your answer. Okay, let's move on to the next question. Oh, geez, there's so many pages. Alright, 5A. Hopefully this isn't too long already. Hope it's not. I don't want it to go above 2 hours. Hydrogen gas can be formed industrially by the reaction of natural gas with steam. Determine the bond enthalpy change for the reaction in kg using section 11 of the data booklet. So, what are we trying to do here? So, bond enthalpies. So we're going to determine, based on bonds broken and bonds made, the overall delta H. So a formula here is delta H is equal to the enthalpy, or the sum of all enthalpies required or involved in bond breakage, minus the sum of all enthalpy changes required in bond formation. So when do we break bonds? We break bonds in the reactants, and so you see here that CH4 is one of our reactants. Now notice, we're gonna need to break all these CH bonds in order to break them, right? So there are actually 4 CH bonds, and if you look at your data booklet, the enthalpy change in kilojoule moles for breaking one CH bond is 414, but we have 4 of them, so we need to multiply by 4. Now we're also going to add this with H2O. There's 2 OH bonds, so based on this, we have 2 times the bond enthalpy for OH, which is 463, minus H2. We have 3 H2s, so we effectively have 3 H bonds to break, and the H bond enthalpy is 436 as well. Or sorry, 436, not 463, 2 different things. And then we lastly have a COO. So this is a weird 2.5 bond order, which is why the question gives it to you. I'm pretty sure it's a 2.5 bond order. Correct me if I'm wrong. I'm probably wrong. But if it isn't, whatever, because the question gives you the bond enthalpy. And because we only have one CO, we don't need to worry about multiplying it with anything. We just have this. And so our question, or our answer, at least what I got, can I erase all this? At least what I got is 197 kJ. Okay. So B. The table lists the standard enthalpies of formation for some species in the reaction above. Outline why no value is listed for H2. So the reason, first let's define what delta HF is. Delta HF is the enthalpy change required to form 1 mole of an element in its standard state. H2 gas is already in its standard state, so there's no enthalpy change required to actually change it into itself. So it's just 0. Now for 2, so that was 1. For 2, determine the value of delta H in kJ for the reaction using the values in the table. Now, given enthalpies of formation, you can actually calculate the standard enthalpy change. This is the formula. I'm just going to write it out because I don't want to butcher saying it. So it's just a sum of products minus a sum of reactants. This is a common theme with a lot of these enthalpy equations. And so what you'll find is, well, what is our products? Our product is, if I can just, our products, well, we have CO, so negative 111, and then we don't have H2. H2 doesn't matter. And then we have H2O and CH4. So that's our products. And the answer you should get is 205 kJ. Okay? So, question 3. Outline why the value of enthalpy of reaction calculated from bond enthalpies is less accurate. Well, remember that bond enthalpies are average enthalpies, or they're enthalpies, yes, that describe the amount of energy required to break a bond, but they're averaged across multiple different compounds. So the actual bond enthalpy between compounds may differ greatly because the value we actually use is an average. So it can be very wrong, or not very wrong, but less accurate, because the values we're using to calculate this final bond enthalpy is from an averaged value. Okay, so C. The table lists standard entropy values. So I'm just gonna see how many pages I have left. Okay, the table lists standard entropy, S values. Calculate the standard entropy change for the reaction delta S in JK -1. So we have CH4, H2O. We have the same reaction. So the formula to calculate delta S is, again, products minus reactants. Remember that. It's going to help you in just about all these weird entropy questions. So, oops. Products. Okay. And we do know these values because they're listed in the table above. So we have 3H2, so we need to multiply 3 here by the entropy of H2, plus 198, which is corresponding to CO. And then 189 plus 186, sorry, not 18, oops. And so the value I got was 216 kJ, or J, not kJ, 216 jk to the -1. Okay. Just trying to see which question I have to do next. Okay, got 216. So for D, calculate the standard free energy. Calculate the standard free energy change, delta G, and kJ for the reaction at 298 using your answer to B2. So now we're relating delta G to delta H. Yeah, so what is the relationship for this? Well, look at your data booklet. I'm pretty sure it says, but if it doesn't, it's this. Delta H minus T delta S. We know what delta H is because we calculated it in B2. It's 205 kJ minus our temperature, 298 K. And then our temperature, or sorry, our entropy, not in J, it has to be in kJ because our delta H is in kJ. So we need to divide by 1,000 real quick, and we will get 0.216 kJ K -1. And the answer I got was 141 kJ. And the reason it's kJ is because, well, K's cancel out. We're just left with an equation involving kJ. Okay, for E. Determine the temperature in K. Determine the temperature in K above which the reaction becomes spontaneous. So this is really just the same question, except now we have to do a little detective work. What I like to do is, in order to determine, in order for a reaction to become spontaneous, delta G must be less than 0. So it requires setting delta G to 0 first before we can do anything else, using the same equation above. Now we know what delta HS is 205 kJ, or it's 205 kJ. We don't know what T is because that's what we're trying to solve for, but we know delta S is 0.216 kJk minus. So if we isolate for T, we get that T is equal to 205 over 0.216, which is equal to 949 K, which means that our temperature must be greater than 949 K in order for the reaction to be non-spontaneous. So 6A. A mixture of 1 mole SO2, 2 mole O2, and 1 mole SO3 is placed in a 1 dm cubed container and allowed to reach equilibrium. Distinguish between the terms reaction quotient and equilibrium constant Kc. I'm not going to write this down, but K or Q gives the ratio of products to reactants at any time at using any concentration, whereas Kc only does this using equilibrium concentrations. Now B, the equilibrium constant Kc is 0.282 at temperature T. Deduce showing your work the direction of the initial reaction. So this involves, because we're not using equilibrium concentrations, this means that we're actually working with our reaction quotient Q. And we know that Q is equal to products raised to the value of their coefficients over reactants raised to the values of their coefficients. The question has given us these concentrations, so I'll just plug them in. So this is just 0.500. Now you need to ask yourself, is Q greater or is Q less than Kc? Well, actually Q is greater than Kc. And because Q is greater than Kc, this means that the reaction must proceed to the left. Okay, C1. Nitrogen oxide is in equilibrium with dinitrogen dioxide. Deduce, giving a reason, the effect of increasing the temperature on the concentration of N2O2. Well, notice, delta H is less than 0, which indicates an exothermic reaction, so heat is a product. What happens when we increase the temperature? Well, remember, by Le Chatelier's principle, we want to alleviate the stress put on the system of equilibrium. So if we're adding more heat, we want to get rid of that heat. So we'll be moving equilibrium this way. And so in return, we are actually increasing the concentration of NO. So because the forward reaction is exothermic, increasing the temperature actually decreases the concentration of dinitrogen dioxide and increases the concentration of NO. So question 2 here. A two-step mechanism is proposed for the formation of NO2. Okay? From NO that involves an exothermic equilibrium process. So the first step is slow, but the second step is, the first step is fast, but the second step is slow, which means that the rate determining step, I'm thinking about this real quick. The rate determining step is actually the second step, which means that the reactants involved that will actually determine the rate come from the reactants of the first step and the reactants of the second step. Now, you need to ask yourself, what is the molecularity of each reactant? So in our first step, we have 2NO N2O2, and then we have second step N2O2 plus O2. This goes to 2NO2. Now the thing is, these cancel out, so they're not important. So the real reactants, so this is slow, this is fast. The real reactants we're interested in are the 2NO and the O2. But because the molecularity of the NO is 2, what we have is squaring its concentration. The molecularity here is this one. So we have O2, the rates, of course, and then rate constant K, which relates the rates to the concentrations of the reactants. Again, you just really need to identify where the rate determining step is, which is the slow step here. which means everything at the rate determining step, all the reactions at the rate determining step and the steps before it are important, and they'll be determining the rate. Okay, so D. The rate constant for a reaction doubles when the temperature is increased from 25.0 to 35 degrees C. Okay. Calculate the activation energy, EA, in kJ mole for the reaction using section 1 and section 2 of the data booklet. So I'm going to try and pull this equation up. Okay, found the equation. So we have that if you look at 6.2, table 1, you have that ln K1 over K2 is equal to EA over R 1 over T2 minus 1 over T1, okay? Now we want to isolate for EA, so we can do that quite easily. So by algebra, what I got was ln K1 over K2 times R over 1 over T2 minus 1 over T1. Now, we know that K2, the rate constant, is twice K1. So we can actually simplify a little bit. Say ln K1 is 2K1, K1 over 2K1, so these just cancel out. So it's actually just 1 over 2, believe it or not. We have 1 over 2 times R, which is 8.31, our gas constant. And then 1 over T2, but I'm going to convert this to Kelvin. So 35 plus 273 is 308. That's our T2 minus 1 over T1, which is 25 plus 273, which is really just 298. And so the answer I got in kJ mole, if I can think about this real quick. 52.9 kJ mole. Okay. 52.9 kJ mole. Okay. 7. Some physical properties of molecular substances result from different types of forces between their molecules. Explain why the hydrides of group 16 elements are polar molecules. 7A. Well, if we look at H2O, H2S, blah, 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 there's actually a difference in electronegativity between the O and then, the H and then the group 16 elements. There's unequal sharing of electrons between these two atoms, which lead to the formation of polar bonds. And these bond dipoles don't cancel out because their symmetry doesn't allow them to do that. Now, if we look at the graph in part 2, the graph shows the boiling points of the hydrides of group 16 elements. Explain the increase of boiling points from H2S to H2TE. Well, if you notice, the molecular masses increase, so the London dispersion forces between these molecules consequently increases. And with increase in London dispersion forces, the more energy you need to break the bonds, and so the greater the boiling point. So that explains the increase in boiling points with increasing molecular mass. Okay. Lewis structures show electron domains and are used to predict molecular geometry. Deduce the electron domain geometry and the molecular geometry of NH2- ion. So let's draw an NH2- ion out. Well, by our valence, by our periodic table, we know that N has 5 valence electrons, H2 has 2. Well, each H has 1, so 2 H's have 2, and then we have an extra minus charge, so 1, so 8 electrons. So if we drew this out, we have N, H, H, So really what we have is something that looks like this. So there are 4 electron domains, which means our electron domain geometry is tetrahedral, but because we have 2 lone pairs, it's actually molecularly, oh my god, I can't talk. With respect to molecular geometry, it is bent, because there are 2 lone pairs, and electron-electron repulsion bends the structure a little bit. Okay, question C. Carbon dioxide can be represented by at least 2 resonance structures, 1 and 2. So calculate the formal charge on each atom in the 2 structures. Okay, so I'll probably just draw this out, which will take me a while, but whatever. So we have the table. The table says structure. So O1 and then O2. And then we have I and then II. So our first CO, how do we calculate a formal charge? For me, formal charge is just should minus has. So how much valence electrons should an oxygen have minus how much does it have in this structure? Well, an oxygen should by default have 6 valence electrons, but it has 2 lone pairs, which means that it has 4 electrons, and then 1 lone pair for every covalent bond. So there's 2 covalent bonds, so 2 electrons, and there's 4 lone electrons, so 4. So 6 minus 6 is 0. Now, if we look at the other O is symmetrical, which is also 0. Now, if we look at the seconds, iteration of carbon dioxide, the second hybrid, the second resonance structure, the first oxygen, it should have 6, but it has 2 lone electrons and 1 electron for each covalent bond, so it has 5 has electrons, and then that gives us plus 1. But the oxygen on the second one, on the second oxygen of the carbon dioxide molecule should have 6, but it has 6 lone electrons and then 1 electron for that covalent bond, so 6 minus 7, which gives us negative 1. So the question in 2 then asks us, well, which one's more preferable? And the more likely structure has to be 1 because each oxygen atom doesn't have a formal charge, and this is energetically favorable. We don't want a formal charge if we don't need one. Okay. So D. Absorption of UV light in the ozone layer causes a dissociation of oxygen and ozone. Identify in terms of bonding the molecule that requires longer wavelengths to dissociate. O3 is a resonance hybrid structure composed of bond length intermediate to double and single bonds, so 1.5 bond lengths. Oxygen straight up has a 2 bond order, which means that there's a stronger bonding in the oxygen molecule, which in turn requires a shorter wavelength of UV light with a comparatively larger energy to break. This one is a lower bond order, which means it has weaker bonds and can be broken using a slightly longer wavelength of UV light, which means the UV light here could be longer wavelength. So in short, O3 contains weaker 1.5 bond order, right, which requires a lesser energy and therefore a longer wavelengths of UV rate in order to break, whereas O2 has a higher order and therefore a weaker bond, or O2 has a higher order and therefore a stronger bond, and so needs to be broken down with a shorter wavelength of UV. Nice. How many pages do I have left? Oh, geez Louise. Okay, we're almost there, I guess. E. I don't want to be wasting too much of your time, so I'm going to try and speed up here. Carbon and silicon are elements in group 14. Explain why CO2 is a gas, but SiO2 is a solid at room temperature. Remember, SiO2 is a giant macromolecular covalent structure which has strong covalent bonds between the Si and the O2. CO2, on the other hand, is held by weak London dispersion forces between adjacent CO2 molecules, and so it's not held together nearly as strongly or nearly as strong, and therefore it is a gas. So 8A, I'm just talking at this point. I hope this is a bit more useful. 8a, the structure of an organic molecule can help predict the type of reaction it undergoes. The Kekulé structure of benzene suggests it should readily undergo addition reactions. 2 pieces of evidence which suggests that, this Kekulé structure isn't actually the structure of benzene. Well, physical evidence. All bond lengths in benzene are the same, 1.5 bond order bond length. So clearly we can't have double and single bonds alternating. The chemical evidence is that benzene cannot undergo an electrophilic addition reaction, which disproves any evidence for a double carbon bond. So that immediately disproves the Kekulé structure. Okay, moving on. Formulate the ionic equation for the oxidation of propene-1-ol to the corresponding aldehyde by acidified dichromate ions. Oh, hello. It seemed like my video cut out at 8b1. I was just in the middle of explaining the question, talking about formulating the ionic equation for the oxidation of propene-1-ol to the corresponding aldehyde by acidified dichromate ions. And so we see that the dichromate ions are oxidizing agents, so they're being reduced, whereas propene-1-ol is itself being oxidized. So this is the half equation for the reduction of CR2C dichromate, for the reduction of dichromate. So we need to also account for the oxidation of propene-1-ol. Propene-1-ol is given generally by this equation right here. If I can just, sorry, my recording software is bugging out. For propene-1-ol, we're given propene-1-ol by this general formula, but it's being oxidized into an aldehyde, which is generally given by C2H5COH. So we need to balance this. Notice that there's the same amount of C's, there's the same amount of O's, but this one has 8 H's, this one only has 6 H's. So we need 2 H pluses here. Okay? It's not 1 H plus, we need 2 H plus. But by doing this, we now have a charge imbalance. Now we have 2 plus here, but 0 here. So we need to balance this. By adding 2 electrons here. However, when we're consolidating these 2 equations, we have to have the same number of electrons in order for things to cancel out. So in order to get 6 electrons in this, we have to multiply everything by 3. So we got 3, 6, and then 6. So this cancels out. The H pluses, so this H plus cancels out. We're left with 8 H plus here. And then we can finally write this out in full. So 3C3H7OH plus Cr2O7 2 minus plus 8H plus 6, the 6's cancel out. Is given by, forms the product 3C2H5COH plus 2Cr3 plus 7H2O. That's what I got. Hopefully that's right. So that's the balance equation. For 2 here, for B2, the aldehyde can be further oxidized to a carboxylic acid. Outline how the experimental procedures differ for the synthesis of the aldehyde and the carboxylic acid. So to get an aldehyde from a primary alcohol, all we need to do is heat under distillation in the presence of an oxidizing agent. But for a primary alcohol to carboxylic acid, we need to heat under reflux. So for question C, improvement in instrumentation have made identification of organic compounds routine. Okay. The empirical formula of an unknown compound containing a phenyl group was found to be C4H4O. The molecular ion peak in its mass spectrum is 136. Okay, molecular formula can be quite easily deduced. We know that we have the molecular ion peak is reflective of the actual molecular mass of the molecular formula. We know what the empirical formula is, and this is just C4H8O, and the total mass of this is just 68.08. And so approximately this gives us 2, which means we need to multiply all subscripts here by 2. So then our new molecular formula is CHH16, sorry, this should be 4. So it would be CHH8O, right? O2. Because we originally started with our molecular formula of C4H4O. We multiplied everything here by 2, and we get this. So identify the bonds causing peaks A and peak B in the IR spectrum. If you look at your data booklet, A occurs at about, I'd say somewhere 1900. So this is a CH bond stretch if you look at section 26. And if you look at B occurs at, I'd say, somewhere around 1700. So this is a COO. It's a carbonyl. So then question 3 asks us, well, deduce the full structural formulas of 2 possible isomers of the unknown compound, both of which are esters. So we know that by that in part 1 we were told this has a phenyl group. So we know for sure this has to have a phenyl group. Now this can only be an ester, and esters have a C with an O attachment bonded to another alkyl group. So we know for sure we have to have an O linkage. Now we know in total we have to have, by our molecular formula here, we have to have 8 C's. So then we can only really afford to have another C. Then we fill with our H's. We have an H here, but we need a double O. So there can't be an H here. We need a double O because our IR spectrum told us there's a ketone group. This is actually stretch B. So now we need to ask ourselves, does this line up? Well, for each carbon, there's one H. So how many H's are there? There's 1H, 2H, 3H, 4, 5, 6, 7, 8. So there's 8 H's. Well, how many O's are there? There's 1, 2. So there's 2 O's. How many C's are there? There's 1, 2, 3, 4, 5, 6, 7, 8. Does this check out? It sure does. So now we have to have another isomer, another structural formula. So this can be done using all the same constituent atoms but in different places. We can have an O linkage here, a C, a double O, a C, so 2C, a ethyl group instead. And this also checks out. Why? Because there's 1H, 2H, 3H, 4H, 5H, 6H, 7H. Oh wait, oops. That doesn't work. Hold on. Let me think about this. 1, 2, 3, 4, 5. 1, 2, 3. Oh, I think I might have drawn an extra C here. That doesn't look right. Okay, let's try this again. Okay, let's see if this works out, because we need 8 C's. So 1C, 2C, 3C, 4C, 5C, 6C, 7C, 8C. So the C's check out. Now we need 8 H's. So 1H, 2H, 3H, 4H, 5H, 6H, 7H, 8H. That checks out. Then we need 2 O's, which we do have. So these are 2 isomers. Now in question IV, in question 4, we need to deduce which structural formula is the one which is the proper structural formula. Which one is the actual one we have? And if you look, there's actually a peak at 4. And if you look at your data booklet, really there is a signal. well, we know that there's a signal at around 4, and between the 3.7 to 4.8 stretch or range, there should be an alkyl group. And let me draw this out just so you can see what I mean. So I'm going to go to my data booklet. And in this range, in the 3.7 to 4.8 range, we have a structure which looks like this. Now we need to ask ourselves, which of these two things, these two isomers, follow this here? Well, to me, it looks like it's the second one here. It's the second one because we have a C double O. So let me do this. We have a C double O. Okay. We have an R group. Oh, no. Wait, I think I'm wrong. I think it should be, I think it's the one right up here, actually. Why? Because we have a C double O. The C double O. We have an R group. We have an O linkage. And then we have a CH, oh, this should be the CH3. And then we have a CH3 group here. I guess this should be this could also be CH3. As long as the order here follows, it seems to make sense to me. So I guess what I'd get is the order I put down was C6H5, COO, and then CH3 was my answer. And that should be it. Okay, so for 9A, organic compounds have isomers, so a straight chain molecule of C5 carbonyl group. So we need a structure with a carbonyl group. But they have to have two possible isomers. So it can't be an aldehyde group, and it can't be a carboxylic acid because there's only really one place you can put those two groups. It has to be a carbonyl group because there are two possible positions we can put these in. This is known as position isomerism. So let's draw out a 5 carbon ketone. So pentanone, I guess. So let's draw that. C 1, 2, 3, 4, 5. So you can have the O double bond occur smack in the middle. Okay. So it can occur smack in the middle, or it can occur offsetted to one of the other flanking carbons, but it can't occur on the last carbon. It can only occur on one of the middle ones. So those are the two possible ways we can draw that. Now, if we look at 2, it says the mass spectra A and B of the two isomers are given. Now explain which spectrum is produced by each compound using section 28. So let me draw these two compounds a bit better. So we had two different pentanones. Just looks a bit like this. So our first one had the double bond here, and our second one had the double bond there. So those are two isomers, and now we have two mass spectra A and B. Now, if we look at the first mass spectra, we see a fragment 29. 29 corresponds to this fragment here. So we need to ask ourselves, well, which isomer 1 or 2 has a CH3CH2 group? And if we look here, it must be 2. Okay, so this one the first graph, the first mass spectra corresponds to this, so this is A, which means the second one must be B, and that's because 43, if I can look at my data book right here, 43 corresponds I believe, to the loss of a CH2, CH2, CH3 group. And so essentially, this works out with 1 CH2, CH3. I'm trying to think how. No, I'm being dumb. No. I messed up. I'll start this again here. So 29 corresponds to a CH3, CH2 fragments. Okay? But that's only here. 1 has a CH3, CH2 fragments, right? It's right here, or it's right here. So this checks out. This is A. The 43 corresponds to the CH3, CH2, CH2 fragments. And this is present here. It's right here. This is the CH3, CH2, CH2 group. So this must be B. So those are the corresponding structures and mass spectra. Okay, B. A tertiary halogenalkane with 3 different alkyl groups undergoes SN1 to form 2 isomers. So the type of bond fission that happens is heterolytic. The type of solvent most suitable for this reaction is a polar protic one, because remember, in an SN1 reaction we have a intermediate carbocation, and a polar protic solvent would help us solvate or stabilize the carbocation by the donation of a proton. Now draw the structure of the intermediate formed and state its shape. So we have a carbocation intermediate and then flanking R groups. And so what we actually have is a trigonal planar geometry. And so in IV, in question 4, it says suggest, giving a reason, the percentage of each isomer from the SN1 reaction. Well, in the second step, a nucleophile can attack. However, this nucleophile can attack either above or below the plane of the carbocation, which means that we're going to form approximately equal, we're going to form enantiomer pairs. But we're going to form approximately equal concentrations of each one, which means that we can say the percentage of each isomer from the SN1 reaction is about 50% each. So the last question here involves nitrobenzene. And you just need to really determine the 2-step reaction process. So if I can read this here, nitrobenzene can be converted to phenylamine via a 2-step reaction process. Okay, so we're gonna have tin. Tin. And tin is going to be oxidized in the process. Nitrobenzene is reduced. No, nitrobenzene is reduced with tin, so tin is oxidized in an acidic solution to form an intermediate ion. So this means we need to formulate an ionic equation for the first step, given that SN, tin, is being oxidized. So what is the oxidation of tin? Well, tin, SN, SN gives SN2 plus 2E minus. Now, we also have to figure out the reduction of nitrobenzene. So this is given by C6H5NO2 to C6H5 NH3 plus. So we need a balance. First. Right away, there's an imbalance of oxygens. There's 2 on this side, but none on this side. So we balance, of course, using waters. So we're going to do plus 2 H2O. Now we have an imbalance of H's, I think. So here we have 5 H's. Here we have 8 plus 4. We have 12 H's. So we need 7 H's on this side, I think. And now we have an imbalance of charges. Yeah, we have an imbalance of charges, which means we have to do something about that. Or actually, let's see what we have. So we have 7H plus on this side, so 7 plus. We have a plus 1 here, so we need 6E minus here to balance that out. Now what we need to do, we need to make sure these the electrons cancel out. So here we have to multiply, to get the 6, we need to multiply by 3. Then we can cancel out. So we can add these together now. 3Sn plus 7H plus C6H5NO2 gives us 3SN2 plus C6H5NH3 plus 2H2O. I think that's right. It sounds right. Okay, I'm going to assume that's right. That's our first step. The second step isn't so hard because it doesn't involve any of this ionic equation stuff. It's a very simple reaction. It's just C6H5 NH3 plus an OH minus. This is the deprotonation step in the presence of some sort of hydroxide, a strong hydroxide. And then this gives us our phenylamine. And well, the OH is pulling off an H here, so this actually forms H2O. And that's our last question. Ugh. Thank you so much for sticking to the end if you did. And if you didn't, that's totally fine. I probably wouldn't either. But if there's any question you have in the future, or any question here that I might have brisked over, feel free to hit me up and I will be able to help you. Thank you.